So what we said previously in the course was that we could find centripetal acceleration in a variety of ways, and I won't go into how we arrived at these equations once upon a time, but we have gotten up to this point already. Then we said, we sort of followed that up just as a conversation point, not to really take us to this level, but just as a conversation point, I said, hey, you know how F equals ma is how you calculate force if you know the acceleration of an object. If you want to know the centripetal force on an object, we call it Fc, then you multiply an object's mass times its centripetal acceleration. So that was just a part of the conversation. I said if you really wanted to come up with a formula for calculating centripetal force, you could just sub each of these AC values into this equation, and you could come up with 3 centripetal force equations. Fc equals mv squared over r, m times 4 pi squared r over period squared, and m times 4 pi squared r times frequency squared. Although really these last two, it's like the third one's a little bit redundant, because really and truly, if you recognize that 1 over period is equal to frequency, it's kind of obvious that the last one is going to be a consequence of the second one. Anyway, that's where we got to a little while ago. I'll let you catch up for a second. But I'd like to go at a scenario, just a really simple scenario to start with, and then we'll make it more complicated. Okay, so I want to walk through a few extra levels of complication here, but I want to start off very, very simple. So in an example, we might have a race car. Traveling around a circular track with a radius of curvature, that just means the radius of the circle is, radius of curvature of 80 meters at 20.0 meters per second. Now let's just say that the car's mass is about 1,000 kilograms. Okay, so nice round numbers. And so somebody might say, I'd like to find out the centripetal force. Oopsie. Acting on the car. And if we were just doing this as a straight question, there's no extra fanciness here. We could just say, all right, so Fc is equal to mv squared over r. I can sub in my values, and I get 1,000 kilograms times the speed we said was 20 meters per second. And you know, I keep on noticing as I look over people's shoulders as they're doing calculations, or as I help people that have troubles, they typically, as silly as it is, they'll write 20 meters per second, but somehow they won't write the brackets, and it'll read on the page as 20 meters per second squared, and so it'll look like an acceleration, so they won't deal with the squared. They'll just do 1,000 times 20 rather than 1,000 times 20 squared. You really got to make sure that you square these values. And so I emphasize it with the brackets, but it's really important to your final result. Divided by 80.0 meters. And a little bit of calculator work. It's going to end up giving you, I think, 5,000 newtons. Okay. So about 5,000 newtons. And if we want to look at sig figs here, we could say 5.00 times 10 to the power of 3 newtons, because I can only be confident about 3 significant figures. There are some people that are messing up their significant figures. They're putting the decimal in the wrong spot. So I've seen 50.0 times 10 to the power of 2. That's wrong. 50.0 times 10 to the power of 2. Numerically, it might work out to being the same thing, but scientific notation has a particular format. There's only 1 digit ahead of the decimal place, so I want to make sure that everybody is following those rules. Before I go any further, I also want to point something out. Fc equals mv squared. Centripetal force is something special. if I draw this car going around the track, the car itself is going to follow a circular path, fine. And people are really tempted, if you calculate FC, I don't want to do it in anything very dark. I just want to use this pencil. They're tempted to draw a free body diagram where the FC is attached to the car. I want to tell you something about FC. FC is not an actual applied force. It's not a force that really exists on its own. FC, a better name for FC, if you wanted to really wrap your head around what it is FC is really F net circular. It's the equivalent of saying F net, but in a circular scenario, okay? So if you ever attach FC to a free body diagram, you've definitely done something wrong, because you'd never draw F net as attached to a free body diagram, and so there's no reason you would ever draw FC either. So I really want to hammer that home. I feel like I say it every single semester, but every single semester there are a few people that don't sort of click in. So I want to try a repeat after me exercise, okay? FC is F net circular. Can you say that after me? I'll say FC and you say is F net circular. Got it? FC is
F net circular.
One more time. FC is
F net circular.
with feeling. FC is
F net circular.
oh baby. Okay, so nobody's going to do that. Don't attach an FC to a free body diagram. Got it? It's the F net, but for a circular force or for a circular motion. So if we have a part A, I want to do a part B. I'm going to take that away, but you guys have the work on your page, so that's no big deal. Here we go. So the next question I'd like to ask to sort of extend this is, what is the minimum coefficient of static friction that will allow this car to stay on the path? And by the path, I mean the circular path that it intends to follow, or the driver intends to follow. So before we really start answering that question, I want to draw a picture. It's always useful to, or it's often useful to draw pictures. So here could be a circular path for a car. Okay? Circular path for a car, and here could be the car that's on that path. Now this is not a free body diagram, this is an illustration, so I'm going to put velocity attached to this thing as well. Instantaneously at this particular time, its velocity might be this way as it goes around the path. So if it's going counterclockwise around this circular path, its velocity might be that way. What direction will its centripetal acceleration be? To the left, right? Like towards the center. So the centripetal acceleration might be that way. Also, if the centripetal acceleration is inwards, you know that the centripetal force is inwards. And again, I'm only attaching this FC to this picture because it's an illustration. It's not a free body diagram. V is upwards, or north, I suppose, if you like, and FC would be to the west. And it wants to follow this circular path. Now, really, some people will say, well, what's propelling this thing forward? Well, at this moment in time, I suppose there's a force of the ground acting on the car. It is pushing it forward. Remember, this is not a free body diagram. I'm just thinking through what all the vectors are. And really, I guess that there is some friction in the axles. So we can call that car on axle, if you really want to be picky about it. That's going to be keeping the car from getting much faster. And I suppose if it's going at a constant velocity, maybe this F ground on car and F car on axle, they might be the same magnitude because it's not speeding up or slowing down. I mean, that could be the case, right? In any case, the only force that's pointing it, or that's pushing it towards the left, it's not centripetal force. What do you think is pushing this thing to the left? What's keeping this car in its circular path? Yeah?
Static friction.
Because that was the question, right?
Yeah.
Why did?
Well, no.
Why?
Because it's in like a frame. If you take it like at an instant, the car is not going to be sliding out toward the outside of the track because the tires are being
Yeah, that's a good point. So at a particular moment in time, you guys know that if we were to grease up this track, you know, if you're going in a roundabout, you know those roundabouts where the cars go around in a circle? If somebody were to pour oil over a particular point on the roundabout, as soon as your car hits the oil, you're going to lose traction, and your car is going to fly off at a tangent. Whatever direction it was driving in last is the direction your car is going to go in. So if you remove friction, your car just keeps on going in the direction that my orange arrow is pointing. You know Newton's first law, objects in motion will tend to stay in their state of motion. Or if you want to think about it as if I take a ball on the end of a rope and I swing it in a circle, if I cut the string at a particular moment in time, the ball is going to fly off at a tangent to its most recent direction of motion, right? It sort of makes sense. It would fly off on a tangent. So if you ever find yourself with a tennis ball on the end of a string and you're spinning it in circles, for example, and somebody cuts the string, you know that the ball isn't going to fly directly away from the center of the circle. It's going to go at a tangent. That's the idea here. So the only force, Connor's right, that's keeping this thing going in its circular motion rather than flying off at a tangent is friction. And so if this is a free body diagram, I got to think about that. So I want to take this car now and I'm going to change my illustration. I'm thinking of the same car in the same position on the track, and I want to look at it from behind. So these are the wheels. Here's the axle. And do you have to draw all this every time you answer a problem like this? No, I'm just talking through the problem so we can sort of hash out the ideas, okay? So here's the car as viewed from behind. There's the wheels there. I know this obviously isn't a technical drawing of what a car looks like, but I want to get the idea across. On this drawing, there's a normal force. There's an FG. And if this is the same car but viewed from behind, what we're proposing is that what keeps this thing turning to the left at that instant in time is a static force that's pushing that way. Now, is the static force an active force or a reactive force? I think it's reactive. It's reacting to the car trying to go off at a tangent. And the wheels are pointed at a certain angle so that the tires will spin and allow it to turn with a certain curvature. But the force involved with keeping it in its circular path is that static force, that static friction force. And it's actually the only force that's acting in that direction. So the centripetal force has to be the static friction force. And we said previously that the centripetal force was, what was the value we calculated it as? 5,000 newtons exactly. And we'd like to find out what mu s is. We're going to have to first figure out what Fg is. And Fg, can you see that Fg and F normal will be equal in magnitude to one another because this is a flat surface? No angled forces or funny business that way. So once I know Fg, I'll know the magnitude of F normal, and then that'll help me find the coefficient of static friction, because Fs, the static friction force, the force that keeps the car from sliding or slipping sideways on its path, is going to be equal in magnitude to the centripetal force, which we already know. Okay? So some quick calculations. We could say Fg, and I chose some nice round numbers here for a reason. The mass of the car that we said previously, the mass was 1,000 kilograms times 9.81 meters per second squared. And you know 1,000 times 9.81, what is it? Beautiful. 9,810 newtons. And so the magnitude, at least, of F normal is going to be 9,810 newtons. And so if we know the normal force, now we can say, all right, so Fs, the static friction force, is equal to mu s times F normal. Mu s all by itself could be expressed as mu s equals Fs over Fn. And now we've claimed already that Fs's magnitude would be equal to the centripetal force magnitude. So I could just sub in the value there. I could say that 5,000 newtons, the static friction force, the minimum static friction force of 5,000 newtons, because the minimum is the minimum friction force required to keep this thing from slipping as it takes its turn. 5,000 newtons divided by 9,810 newtons gives us a static friction coefficient value of, did anybody calculate it yet? Naz?
0.5097.
0.97. That sounds about right. And I want to take it to 3 significant figures. So I'm going to have to say 0.0510. Okay? So the minimum coefficient of static friction that we could have here in order to stay in a circular path would be 0.0510. Now, if I want to do it, have more static friction than that, if I want to have more static friction than that, am I going to slide? No. But the minimum that I need is that. Okay? So if I want to know what the minimum static friction coefficient is, that's the minimum. If I've got a static friction coefficient of 0.23, I'm definitely not going to slide. How could you increase the static coefficient friction for the surface junction between your tires and the road? Yeah? Okay, so make it have a rough road.
Yeah.
What else could you do? Yeah?
Warm up the tires.
Warm up the tires. So in the summer, actually, your traction is better. So warm tires. Now in the winter, your tires are cold. So what else could you do? Yeah? Okay, so we said rough up the road before. What about roughing up the tires? Better tread. That's really what tread is, just roughness of tires. EAD for tread? Oh my gosh. Spell check has ruined me. So you can change the tread. So people talk about getting those winter tires, and you know, and nobody ever thinks this way, nobody goes to Canadian Tire and says, hey, I need to get some new tread, I need to get those winter tires for my car because I got to increase the static coefficient of friction between my tires and the road, eh? Nobody ever does that. But that's what they're doing in effect. They're going and getting these winter tires. And you don't keep the winter tires on your car in the summer because what happens to the tire? Does anybody know?
Tread wears.
Yeah, the tread wears. That softer rubber, that tire with that different tread, it wears more. Now what makes it sticky and grippy in the winter is what makes it wear out in a hurry in the summer. So that's okay. You just rotate your tires. Maybe you have 2 sets of tires. Not everybody likes to do that. They try to ride the middle of the road, which is the all-season tires, which is cheaper, but not as effective in the wintertime. So that's one thing that we can do is increase the coefficient of friction here. Now if I go back to my equation that we were looking at on the previous part of this question, and I don't want to add anything to the actual solution here, but if I go back here, and if I say that I can increase my friction force, what else can I increase? Can I go faster around corners? Sure, if you want to. So you could go faster around the corners. If you were somebody that knows that all the people around have these really grippy tires, now maybe this isn't a fair assumption, but let's say that everybody by law had to get winter tires in Canada. That's not a law, but if they did, could the road engineers change the on-ramps? Could you change the radius of curvature on all the on-ramps to make them tighter so we waste less land? You could. I don't think they're ever going to do it because I doubt that they're going to make that law. But if I wanted to make this R value smaller for an on-ramp, look what happens to the fraction. If I decrease the denominator, what happens to the fraction as a whole? It gets bigger, yeah. So you could actually hope for getting more centripetal force and use more, if you were able to supply more friction force by having better tires. You could do that. We would change the way we design our roads. More commonly, what road designers do is they make the R value really big. What that means is the on-ramps and the off-ramps for our highways have a really big swathing curvature to them. The very wide curves that the on-ramps and the off-ramps have. The reason they make that R value really big, well, you tell me, what happens to this fraction if you make the denominator small? It makes the whole fraction's expression get smaller. So if the R value gets bigger, the required friction force gets smaller, which means that people can still drive safely even if they have crappy tires. Which I think is probably a good thing because the assumption being is that not everybody is going to be very good at maintaining their tires or choosing to get the best tires. So this idea of having wide curvatures to our on-ramps and off-ramps actually saves a lot of money for people having accidents and things like that. Even so, they do put those concrete blockades around the perimeter of the on-ramps and off-ramps so that people that still decide to go ridiculously fast and not slow down when they get to the off-ramps don't cascade off into a ravine or something like that. So there is provision for the people that are even less reasonable than you would hope. I'm trying not to say a bad word, but you know what I mean, right? So we have these barriers so that even the people that do slip, or maybe they lose control for whatever reason, don't go off into a ditch. Does that sort of make sense? Maybe I have a question about that? Okay.